Hi. Just getting our earthquake thing in case you want to ask questions on it. All right, today's the 2nd of March. And it's 11:30, 12:15. Super. Okay, who's there? Oh, nobody's there. There's Teresa. Good morning, Teresa. Let's see if I got some other folks coming. But I got Teresa and Ellie. Good morning, Ellie. So Teresa and Ellie. Soupy. I'm going to put what we're doing while we're gathering up, okay? We're going to talk about shadows and two laws, law of reflection and the law of refraction. Yeah. I need a sun today. I wish I had a yellow marker, but I don't. What am I going to do? Okay, it's going to have to be a red sun for today. Okay. All right, I'm hoping we still got another person out there, Zach or Anne-Sophie. Can you hear me? Okay, Ellie and Teresa, I have already posted the earthquake worksheet. You can take a look, maybe you have already, and see if you have any questions on it. I'm happy to answer questions either today or the next time we meet. So that would be just fine. I'll have it due, I think it's Friday at 4 in the afternoon. It should give you time to work on it. If you get stuck in between times, you can always just email me with a question, ask me for clarification, or if there's something you don't understand, I'm happy to help you. Okay? You do not need to feel like you're alone in this online world, which you are theoretically. There's Zach, super. And I'll say the same to Zach. If you have questions on the earthquake sheet, feel free to email me at any time, Zach, and I'll try and get back to you to help out with that. It'll be due Friday, and it's more or less a review assignment having to do with waves and resonance and stuff like that. Okay? Okay. I think you'll like it. I think it's an interesting one. So let's talk a bit about shadows. So let's get to our topic of the day, one of our 3 topics. And I'm going to do this with you by thinking about a solar eclipse. Solar eclipse. Solar eclipse. So here's the sun. This will not be to scale, as they say. In other words, the sun and the earth are millions of miles apart. I can't draw them that way. So you'll have to kind of bear with me a little bit. So there's the sun. Draw yourself a sun. Here's the earth. Way too big compared to the sun, but what are you going to do? I need it to be big to show you something. And what's missing, folks? What's missing to make this solar eclipse happen? to complete my picture? What do I have to draw? And maybe where? What's missing for my picture of a eclipse? And I wonder if any of you have seen an eclipse. I saw one when I was a boy. The moon, thank you, Ellie, exactly. So here we go. The moon, I'm going to put very carefully, and I hope this will work. And what I'm going to do is I'm going to try and draw some rays of the moon. And it kind of goes like this. Let's pretend the sun's rays are coming like this. And like this. Okay, so the sun is so big, exactly, in front of the sun. Thank you, Ellie. That the sun is so big compared to Earth that, frankly, a lot of the rays go right around the moon. Here's the moon. So the trouble is, the moon is blocking a fair amount of the sun from this direction. So I can add some other rays coming from this part of the sun. And say, oh, okay. So this part is being blocked. Okay. The part of the sun from this portion of the sun is being blocked over here. And then I can do the same thing with the other side, okay? If I start here, yeah, that's going to work okay. What I get is, and I better do this, I'll do this in green, I guess. I'm kind of out of markers. My black's not working so well today. This spot that is totally blocked by the moon, that spot there, I'm going to put a little, let's put a little star there. If you were standing at that spot, that would be a total eclipse. So that the moon would completely block the sun's light. And in terms of science, it's called an umbra, which is the Latin word for shadow. So you're in the umbra. Now, if you're in one of these other spots, I guess I'll do it in more blue, maybe more red. Red is a crappy color. I'll do more blue. So if I'm over here or here, and I'll put a little star by each of those, a little blue star. This you might have heard of too. It's called a partial eclipse. And it's called then being in the penumbra. That's the word for partial. So the deal is the penumbra. Ooh, I'm wondering if Anne-Sophie is out there. If you can say hello, Anne-Sophie, that'd be great. Otherwise, sometimes I know that you can't. Just write me an email or something. Okay, if you're in the penumbra and you look up at the sky, you're going to see the sun. Maybe I'll do it over here. If you're in the penumbra, you're going to see something like this. Okay, you're going to see the sun partially blocked by the moon. You know what I'm saying? So that's the deal. So only part of it is blocked, so part of the light is still getting through. It'll be a little bit darker, but not fully dark. Now, can I ask, have any of you been in a spot with a total eclipse? Have any of you been in a spot with a total eclipse? So yes, no? I think so. Oh, okay. Cool. Elliot, were you young? Do you not remember so well? Because that happens too sometimes when we're very young. Ah, Teresa too. Wow. Because I often have the case where most of my students have never experienced this. Here I got at least two who look like they might have. Elementary school. Far out. Okay, now, if it really got totally dark, then the only thing you'll see is, to be honest, sometimes you'll see little rays of sun coming around the edge of the moon. It's weird, but it's pretty dark. What's cool about it, among other things, so Teresa also saw it. What's cool about it is that you'll hear the birds sing if you got birds around. It's that time of year. In other words, they think it's either getting dark, sunset, or they think it's sunrise. So when it ends and you start to get into the partial eclipse portion, the birds start singing because they think it's morning. Birds are birds are smarter than we think, but in this case, they don't really know what they're doing because they think that nature's making it sunrise even in the middle of the day. So that's just their response is a response to light or a lack of light in the case of sunset or sunrise. Kind of fun, huh? Kind of weird. Birds singing, middle of the day. Anyway, yeah, so that's a bit about shadows. Okay. The other thing that can happen is, of course, I can get a lunar eclipse where now the Earth is blocking the light to the moon, of course. So Earth is blocking the sunlight, as it were. However, I often get some indirect sunlight shining off the Earth. We call it Earth shine instead of moonshine. So you'll still see the moon. It looks kind of reddish. So the moon does not look totally black. Moon not totally dark, because even though it's not getting direct sun, it gets some earth shine, usually off of parts of the earth that are lit up by the sun. It's a bit complicated on a whiteboard, but you'll still get some earth shine rays coming off here from parts of the earth. Earth shine. As opposed to moonshine, right? Or moonbeams, you get earth beams if you're on the moon. Ask the Apollo astronauts. They actually did see some earth shine, as it were. So moon not totally dark due to moon due to earth shine. Which is kind of weird. Or earth light, you could call it, instead of moonlight. So you might have seen a lunar eclipse. They're not as spectacular, but they're kind of cool. The moon definitely gets a little darker. Ute, questions from you about shadows? Of course, we have shadows as well, and you might have noticed this if any of you've been in theater productions, that you can also get places on stage that are completely dark, right, in an umbra, and other places that are partially dark, okay, from different spotlights. So this is actually not just with eclipses, but often stages, you'll have areas that are in the umbra or penumbra in the stage and planned that way. So the different actors have different amounts of light on them. Yeah? Okay. So it does have some practical uses on Earth as well. Okay. Ute, Now, we're going to talk about two laws. I know the law of reflection you all know. Okay, I'm sure you know it from math class and whatnot. And I'm not trying to insult your intelligence because we need a couple of names from that law that we'll use in the next law, the law of refraction as well, which is a little more challenging. Okay? So I'm not trying to insult you by telling you about the law of reflection. I know you know it. Okay? But let's do a diagram and you'll see what this is about. So officially, the law of reflection says that the angle coming in, called the angle of incidence, I'll try and spell that carefully, the angle of incidence, the angle, I'm going to use the symbol for angle now, of reflection. And of course, what fills in the blank, okay? You tell me here, what's going to be the angle of incidence? That's the incoming angle. The angle of reflection. Please put your answer in now. The angle of incidence, the angle of reflection. Then we're going to sketch that because we'll need the terms for the future. Okay, I know you're trying to take notes at the same time, but maybe you got a good guess for these two angles. Tell you what, I'm going to draw it while you're thinking. Maybe you're writing and I'm just not seeing it because of the lag time. Here's my surface. Let's say this is my mirror. Here's my incoming angle. Let's do it in, I don't know, red, I guess. Now let's do it in green. My incidence angle. And once that hits, then, thank you, Teresa, is equal to, like I said, I know you know this. Bear with me. I'm not trying to insult you all. They're the same. Exactly, Zach. Right. Thanks, everybody. Okay, so here comes in, and that's the angle of incidence. Well, let's call this is the ray. So I'm going to call this the incident ray. That's the actual line, okay? So it's coming in, boop, it's the mirror, and then it goes out at the same angle. I hope that's reasonably close to the same. And we can call that the reflected ray. Reflected ray. Now, here's what you may not have known. There's a special line that they draw the angles from. And you might have this in math class, I don't know. You've got to draw a line perpendicular to the mirror, right where the ray of incident hits the mirror. So draw that with me. I'm going to make it like a dotted line. So straight up. And when we do refraction, we'll have it go down as well. But that line that's going straight up is called the normal line. And the angle that they measure, the incident angle, is this one. It's from the ray up to here. And then the other one, so this is the incident angle. Incident, I'm going to abbreviate to INC. No, I'm not. How about INCID? Incident angle is this angle here. And then the one going out, I do that in blue, should be the same amount. And of course, it's from it's from the reflected ray back to the normal, and that's the angle, whoa, that's the angle of reflection. Reflect. Okay? So this normal line really is perpendicular or normal. That's the old-fashioned word for perpendicular in math class. It's normal to the mirror. So I can draw a little right angle like that. Okay? So not surprisingly, this law holds for mirrors and all sorts of other stuff. Okay? Like I said, not so interesting. Oh, move my legs here in my little tiny studio. Now, okay, all, whew, yeah, we can get rid of that. All waves follow this law. Although with an earthquake, I don't know, I don't know what they would bounce off of. Ah, thank you, Ellie. So Aunt Sophie's writing a clausura. Okay, I somehow missed that one. Appreciate it. Okay, but we're talking about radio waves, so light waves, sound, water, um, bat waves. Of course, bats use that, right? And so on as well. Okay. However, just be aware of one little weird thing. The image, that's the thing you see once it's reflected. In other words, if you're looking like this, there's your eye, there's your eyelashes. Okay. If you're looking this way, is inverted. In other words, and you know this from math class, so I know. If I reflect something like this, it's going to come over and it's going to look like this, right? You know what I'm saying? So it's inverted. So, okay, there's the image. And this, if we ever get to do some labs, I hope I can do labs with you, then this is called the object. We're going to do some labs with those, especially when we get to lenses, which is not so far away. So there's the image and there's the object, okay? And so this thing is inverted. If I go like ABC, then it'd be ABC, then be ABC, only if I go the other way around, right? Yeah, we often say the image is reflected, but inverted is another way to think of it. Turned around. Yeah? Okay, good. I want to talk about paper for a second. Paper. Yeah, we haven't talked about color yet either. Color's pretty cool. Let's get rid of all this. We are going to talk in depth about color, maybe next time when we have a little more time. But for now, what do you know about white? White does what with the light that hits it, as opposed to like black? Like I have a sweater that's black, so white, light. And if I wear something black, black, light. So what do white and black do, folks? Yeah, it reflects light and black absorbs. Thanks, Ellie. So Indeed. So if I got white, whether it's the whiteboard or the white piece of paper, it should reflect light. But if I like black, like my sweater here, and I go out in the sun, it will absorb light, which sometimes feels good, right? Again, we're going to come back to color. But the reason I mention that is we need to talk about a piece of paper now. The paper's white. Why can't I see myself in the paper? All right. So what's the deal with the paper? It should like show me like a mirror. Why not? All right. So let's kind of figure out. So here's a piece of paper. I'm going to write paper is white, but let's see what happens. The surface of paper. Run my fingers across it. It's smooth, but it's not like a mirror or a glass or anything like I can rub my screen. It's not that smooth. So to be honest, paper is a little tiny bit uneven. So watch what happens when the light comes, okay? So the light comes, I'm just going to show you. Here's a ray, boom, and maybe like this. Here's another one, but maybe it hits a spot in the paper that's not quite flat because it's a tiny bit bumpy. It goes like this. Here's another one. Maybe it's like get a spot that has a little hill in it. It goes like this. And another one here that's parallel. And it goes like, I don't know, maybe like that. So what I get is no clear image. Especially if I take some parallel rays. My writing's really sloppy. These are supposed to be parallel. So these are parallel incident rays. I drew 4 of them. And they all land at different spots in the paper, and it's a little uneven, so they don't make a nice clear image like a mirror does. With a mirror, that's easy to draw, isn't it? With a mirror, the rays behave really well because it's so smooth. We just go ba-dum, 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 ba-dum. Okay, so the image is clear. That image is often you, right? As we use a mirror. Isn't that kind of cool? So it really matters how like smooth it is. When I get paper with no clear image, we call it a diffuse reflection. That's the science name for that. Diffuse means not so in one spot. But a true reflection happens with a mirror. And that's why. It's the difference in smoothness that allows us that quality. Good. Let's see if there's any other fun stuff that I can tell you about. With reflection, I think we kind of got it. This diffuse reflection is not always a bad thing. Let's talk about sound for a second. That was about colors and stuff. Let's talk about acoustics, right? Which is the study of sound. Pardon me. Let's say here's our room. And let's say here's our stage. Think of the aula, everybody. Think of the aula. There's the stage. Well, if I got somebody playing an instrument or in a play, then what can happen is I can get the sound come out and it can reflect several times. Why am I doing this? So for you sitting here in your chair, right? There's you in your chair. And you're trying to watch this. Too much sound. So too many reflections sounds echoey. That's not a very scientific word, but I think you get what I mean. There's too much sound. It does not sound good. It's actually hard to listen to and understand what they're saying up front. Okay, let's draw a new room. Okay, so let's say you do this and you have, you decide you want to put up some panels to try and get rid of some of this sound. Too many echoes. Well, I can also have this happen. I can have spots where so much sound is absorbed, especially if it's behind something. Here's my stage again. So that then I can get some spots on the back of the room. Maybe I'm behind a post or something, whatever a post looks like. And my chair's back here. That would be a pretty bad chair. I can get dead spots. At some theaters, there will be seats that are extra cheap and they're not good. They're dead spots. So be aware if you go to like an old time theater for an opera or something. Not the modern opera house, but some of the older ones, okay? So you want to avoid that too. If you're an acoustics engineer, then you want a nice amount of sound throughout the room. Think like Philharmonie, if you've been in the Philharmonie, or think of our new aula. Now, you guys may not be remembering, but before the aula was renovated, it was awful. It was awful to sing in, and it was awful to try and listen in because it was very echoey. And I'll just say, study of sound. The aim is to have enough sound, and they do this by studying reflection, frankly. Throughout room, or throughout the hall, let's call it, like the aula or the theater room, have enough reflections throughout the hall, but no dead spots. So you get a beautiful, smooth, what's the word I'm looking for? A beautifully dispersed sound that sounds good from everywhere in the room. That's kind of the study of acoustics are. And I'm proud to say that our aulas now kind of like that. They put some stuff on the, you ever notice that? They put some panels up on the ceiling. That's why they did that. It was the acoustics engineer that did this for the school. So it's pretty good because of that reason. Yeah. Good. Yeah. So that's how the law of reflection is used by acoustics engineers to get just a nice amount of echo, but not too much feedback or anything unpleasant to make it hard to listen in the room. Huge. Huge. Let's go on to refraction. Refraction. And this is what I hope I can get a lab and have you do this next week. Wouldn't that be nice to actually see? I hope we can do this, my people. So this would be then a week from Thursday. We could maybe do our first lab. Cross your fingers, huh? Cross your fingers. So let's talk about refraction. And as you might know, that's the bending of light. Bending of light when it changes. And let's see if you know already. Probably you do. Can you fill in the word? So light bends, that's refraction, when it changes. Think of a wave. What could a wave change? It could change the. And we're gonna draw this in a second as well. So light bends when it changes. Ellie, I love it. Medium. Thank you. Example, what we're going to do in our drawing is do from air to water. And we're going to use a light ray. Sound waves refract too. Ocean waves refract too. Earthquakes refract too. So it's not only light, but we're going to do it for light. Okay? So we're going to see the light, hopefully, very soon. Okay, here we go. Here's some water. Here's our normal line. So we got to draw a line that's perpendicular to this water. There's our normal. And we're going to draw a ray. Okay, so I'm going to draw a ray coming in. Probably don't want blue, I guess green. So let's say my ray comes in like this. And I'll put a little arrow. So that's my incident ray. And the angle we're going to claim is this one. So the angle to the normal will be the incident angle, okay? There's my little math symbol for angle, okay? So there's my incident ray and my incident angle. Now, as you probably know, some of that light actually reflects off the surface. You probably know that, but we're going to ignore that part for now, and we're going to say, okay, what happens to the light when it goes down here? And as you probably also know, it doesn't go straight. It doesn't go straight like this. I'll just cross that out. What's your guess? Does it bend towards or away from the normal? Let's see if maybe you've had this before. Which way does the light bend once it gets into the water? This is water down here. Water, air. Okay? Which way does it bend? Towards or away from the normal? What do you think? Away from the normal. Second guess? It actually goes towards the normal. So it goes kind of like this. And now my angle, so this is my, we're going to call this my refracted angle, refracted ray. And the angle is right here. and it's lower. So the law of refraction, if I could say this, we're running out of time, so I want to write this in clear words before we go. The law of refraction, I'll put over here, is kind of like this. When a wave changes to a denser medium, here we could say optically denser, but I don't need to say that because it's not always about light. So I'm going to say a denser medium. The refracted angle is less than, you can write that in symbols if you want to, is less than the incident angle. Turns out, vice versa. If a ray's going out from, let's say you're underwater and you're a fish, if a ray's going out, once it gets outside, it bends then away from the normal and heads this way. Well, this is kind of interesting if you're a fish. And I think I'm not going to have time for the whole fish story, but let's do a little bit of fish. Have you ever been in a pool or lake and you go underwater and you look up? What do you see? It's definitely not going to be 360 degrees, or not 360, 180 degrees. What do you see when you look from underwater up at the surface of the pool? Sorry, my nose keeps running. Well, we're going to sketch that as you think about that. If you're a fish or a person underwater and you look up, what do you see? Okay. I got to start with a clean picture. So I'm hoping you've got that more or less drawn. Well, it turns out if you're the fish, I'm going to make you a happy fish. There you are. And you're looking up. Here's where you're looking is the normal. Okay. You can see from your eye there about 46 degrees. And once I get past that, ready, watch this. Here's more of the water. Once I get past that, it just reflects like this. In other words, the light doesn't go out anymore. And like this one will go out and go like this. And if I do some other ones, the fish can see up here too. And then it reflects not towards normal, but away from the normal. I can even go up and do another one and really show it going away from the normal. Okay, so that's what the light's doing from the fish. Until this angle right there, 46 degrees. So after 46 degrees, all the light after that time reflects. So I'm going to say beyond 46 degrees. You'll see why I'm saying this to you in just a sec. All light reflects back, reflects down. I'll just say reflects. But it's the same in the other degrees, 46 degrees. Same here. So the cool thing is, if you're a fish, you know how humans, we can see like 180 degrees, right? We call it our horizon. The horizon of a fish looking up at the surface is not 180. It's 46 plus 46, which would be 92 degrees. So fish, or you, if you're underwater, or you see a 92-degree horizon looking up at the sky. Hey, I know we're in winter still, or late March, and I know it's a minute past. I'm going to end this just right away. But once you're in a lake or a swimming pool again, go underwater, just look up from like a half meter or a meter below the surface, and you're going to see it's just like this. It's weird. It's like a sphere. Of course, it's not two lines, it's a sphere, but it's a sphere that's 92 degrees in all directions. Not cool? Learn something neat about physics. So look forward to that in spring or summer, whenever you can get back in a pool. Thank you, everybody. Enjoy the rest of your day, and ask me questions if you got questions on the earthquake stuff, okay? Stay healthy, be well. Bye.